Hi everybody. So this one's been a long time coming here. So this is Chapter 4, Problem 84 was a question here. So it says a proton in a synchrotron, whoa, is moving in a circle of a radius 1 kilometer. So that's the radius. It's 1,000 meters, increasing its speed by this equation. So this is a speed equation where they're giving us some constants, C1 and C2. So C1 plus C2 times t squared. So the constant C1 is 2 times 10 to the 5 meters per second, and C2 is 10 to the 5 meters per second cubed. So those are just constants to make sure that the units work out. So now it says, what's the proton's total acceleration at 5 seconds? So, all right. So let's say the proton is right here. That's where I'm going to say it is. So it's going to have some acceleration pointing up. That's going to be tangential acceleration, right? That would be the speeding up part of it. That would be caused by that equation up there. But there's also going to be a centripetal acceleration as well. And then the total acceleration, using Pythagorean theorem, because I could add up these two vectors, if I have centripetal plus tangential, the total acceleration would be pointing this way, and then I can use Pythagorean theorem to find out what's the magnitude of that total acceleration. I'm going to, well, let's see. I could write this two ways. If it's the magnitude, I would just get the total using this. So Pythagorean theorem, it'd be the tangential squared plus the centripetal squared. But I could also show you how to if I find the acceleration using bracket notation. So I'm going to assume that they say total acceleration. I could just use bracket notation. That'll be that. So maybe I don't need to use the Pythagorean theorem. But anyway, okay, let's get into this. So I want to try and find out. So this is all part A. I don't think I'm going to use this now anymore. So I want to find the total acceleration, and I have the velocity function. So how do I get the total acceleration with the velocity function? Well, I could take the derivative, because the derivative of the velocity function is going to give me the acceleration. So if I have that the velocity function are these constants, C1 excuse me, plus C2 t squared. So the derivative here, C1 is just going to go away. That's just a constant. So the 2 is going to drop down. So it's going to be 2 C2 times t. And that's going to be my acceleration, but that's my tangential acceleration. So I can then find out my tangential acceleration at 5 seconds. So that's 2 times C2, which is 10 to the 5. And then I multiply that by 5 seconds, because that's what the question's asking me for. And I get another 10, so it's 10 to the 6. Meters per second squared. Or 1 times 10 to the 6, or whatever the heck you want to. So that's my tangential acceleration. Let's hold on to that. Now I need to get my centripetal acceleration. So to get my centripetal acceleration, I know any centripetal acceleration is the speed at that moment squared divided by the radius. So I know the radius, it's 1,000 meters. But now I need to get the speed at that point. Well, luckily I got an equation that'll tell me the speed. So I just need to plug in 5 into that equation. So let's go ahead and do that. So my velocity at 5 seconds, that's going to be C1, which is 2 times 10 to the 5, plus C2, which is just 10 to the 5, multiplied by t squared, which is 5 squared. So I'm going to do all this on my calculator on my phone here. So I got 5 squared, that's 25, times 10 to the 5, plus 2 times 10 to the 5, and that's going to be, I'm getting, let's see, looks like 2.7 times 10 to the 1, 2, 3, 4, 5, 6. 2.7 times 10 to the 6. So this is a speed of 2.7 times 10 to the 6, which is good. We're still in range if we're not overcoming the speed of light barriers. That's in meters per second. And then I'm going to plug that though in for here. So that's going to be 2.7 times 10 to the 6 squared divided by my radius, which is 1,000. So my centripetal acceleration is going to be about 7.3 times 10 to the 9. And that's meters per second squared. There we go. So if I want my total acceleration, in this case I'm just going to use bracket notation. So it's going to be, let's see, what I have here in my x direction, I have my x pointing to the left. So I'm just going to say it's negative 7.3 times 10 to the 9, comma, the tangential acceleration is 10 to the 6, and then meters per second. So if I wanted to, I could get the magnitude of this as well. I could just use Pythagorean theorem like I was going to do up here, but they just want the vector. So if they want the vector, then really all they want is this. And I think that should be sufficient. And this is all based on my diagram too. If I just said that the dot was there, but if the dot was here, the dot could be here. It's up to you. But yeah, okay. So there you go. There goes that. Then the second question says, at what time does the expression of the velocity become unphysical? So unphysical, and I gave you the hint that nothing can travel faster than the speed of light in a vacuum. So the speed of light in a vacuum. So speed of light in a vacuum, we call that c, is 3 times 10 to the 8 meters per second. That's my hint that I gave you. We'll talk about why that is second semester as to why that actually is. So basically I want to set my velocity equal to c, so equal to 3 times 10 to the 8, and see at what time that occurs at, because then any time beyond that basically means that I'm just going to have a bigger velocity, and that just can't be the case. Again, physics does not allow this. So alright, so again I'm using this equation, my velocity, and then c1 plus c2 times t squared. So I'm just going to plug in 3 times 10 to the 8 in there, equals c1 is 2 times 10 to the 5, c2 is just 10 to the 6, I think. Nope, 10 to the 5. And then t squared. So let's see, I'm going to subtract both sides by 2 times 10 to the 5. So 3 times 10 to the 8 minus 2 times 10 to the 5. And then divide by 10 to the 5 equals t squared. I want to take the square root of both sides. So that'll give me the square root of 3 times 10 to the 8 minus 2 times 10 to the 5 divided by 10 to the 5 square root. That'll give me my time. So let's plug all that in there. Again, I'm going to plug this into my calculator. 3 times 10 to the 8 minus 2 times 10 to the 5 divided by 10 to the 5. Take the square root, and that's happening at about, looks like I got about 54.8 seconds, or 55-ish. So that's the time at which that this becomes unphysical. So basically what we have here, what I'm kind of talking about, again, this is beyond what we've done if you've taken physics in the past before. We have a model for some particle that's moving that obeys this model right here. However, the model is going to fall apart. If it goes to what we call relativistic speed, so that's speeds that are close to the speed of light in a vacuum, 3 times 10 to the 8 meters per second, the model falls apart. It doesn't work anymore. We got to use a different theory, or a different, which is the relativistic theory, to then use its models, which tend to be more complex, to describe this particle, better describe this particle. So yeah, I don't know. I just thought that was kind of cool, because kind of showing of how, you know, we can have a model, and the model is very good. The model can often predict things, you know, at speeds that are practical. But however, there are points where all models will just fall apart, and you need to pick it up with another idea. And that's where this model falls apart, is when it reaches those speeds after about 55 seconds. So yeah, all right. I don't know. I thought that's cool. If you don't think it's cool, well, I don't know. I'll see you later. Bye.